Good afternoon, everybody. My name is Stanley Kateguru. I'm a trainer here at NTI, and I'm in the electrical workshop at the moment. This afternoon, I would like to introduce to you one of the most important electrical machine, which is called a three-phase induction motor, the one I'm holding at the moment. This is a very popular electrical machine in the sense that most of the industries that you go to, you will see that they will be making use of this machine. Now, today, my main objective is to try and introduce to you how you can quickly determine whether the motor is functioning properly or it has been damaged. Okay, the main parts of an electric motor, as you can see, is what we call the stator, which is the outside body of the machine, and this is a fan cover. There's a small fan inside, that white thing you can see inside, that's a fan, and there's the rotating part of the machine, which is called the rotor or armature. This is the part which rotates. So inside, around the stator, we've got stator windings that are wound in there, and we have a terminal junction or a terminal box right at the top where we make our connections, where we connect our three-phase supplies so that the machine can run. So what I'm going to do right at the moment is open up the junction terminal box, so the terminal box, so that we can start testing the windings that are inside. The three-phase motor is made up of three windings that are separated from each other by 120 electrical degrees. So what happens is when you connect your three-phase supply, that's the red, yellow, blue lines, you notice that a magnetic field is going to be produced around the stator, and it will start rotating at what we call a synchronous speed. That's the speed of the rotating magnetic field in the stator. Now, because the rotor has also some rotor windings, it means this rotating magnetic field will be cutting the rotor windings, thereby inducing an EMF, according to Faraday's laws, which says that whenever a conductor cuts or a magnetic field cuts a conductor, an electromotive force is induced in that conductor. So as soon as we connect our three-phase supplies into the stator windings, automatically a rotating magnetic field is created and it starts rotating at synchronous speed, which is the speed of the rotating magnetic field. So that magnetic field starts cutting the windings of the rotor, because the rotor has also some windings in it. So it starts cutting the rotor windings, thereby inducing an EMF in the rotor windings. Now we have got two fields. The one is a result of the stator, and the other one is a result of the rotor. So what is going to happen now, two magnetic fields, these two magnetic fields are going to interact, and a torque is produced. Then the motor starts turning on its own automatically. So that makes it a very reliable and easy machine to run, because it can start on its own. Right, so what I'm going to do now is to use one of these machines. I'll start off with a multimeter, which is measuring instruments that we use to measure the resistance of windings. So it is possible that the windings can be open-circuited, and once they are open-circuited, then it means we've got we don't get a magnetic field into the stator, and the motor will not be running. So we need to check or to test and see if the windings are continuous. All of them, there are just three of them. So we must test each and every winding. First and foremost, to see if they're not open-circuited. And secondly, to see that the rotor windings have got the same resistance, because this is a three-phase load, which means we should have the resistance of the windings equal throughout. Okay, so first winding, second winding, third winding, we should have the same value of resistance throughout. So what I'm going to do here now is to switch on the multimeter. So I'll select the ohm scale so that I can measure the resistance of each and every winding. Okay? So first of all, I have to identify the beginning and the end of the winding. So I'll put one probe of the winding on one position and another one on the next. As you can see there, I'm getting a very low resistance. There are actually some short-circuiting bars that are inside. I have to remove them. Okay, if I tilt this machine this way, and probably everybody will be able to see well. Okay. Okay, so these are the short-circuiting bars. I have to remove them. I have to take them out so that we can start the measurement. So sorry for that. I have to remove the short-circuiting bars first. Okay, welcome back. Now I'm going to carry out the measurement of the winding resistance using a multimeter. The fluke type is the best type you can get almost all over the world. So we have got here a fluke 87, and this instrument can assist us in determining the resistance of each winding. So I'll start off with the first winding. I'll put one point there, and another one I'll put it on the last one. And if you can see that well, there's 3.1 ohms. That is the resistance of the first winding. So it means this point is probably the beginning, and that one is possibly the end. And the winding has been done right round inside the stator winding to produce that. So I'll now go on to look for the second winding, and fortunately it is the middle one and the end one right at the top there. It is giving me almost the same resistance again, 3.1 ohms. So I can go on to measure the last resistance or the last winding resistance, which is most likely to be these two here. Again, they give me the same reading, 3.1 ohms. It means the resistance of the windings, of the stator windings here, they are balanced because they are of the same value, all of them. What it basically means is when current starts flowing, when we make our connections or we supply these windings, the current is going to be the same in all the three windings. But what happens is actually the three currents will be displaced by 120 electrical degrees. So they are of the same magnitude, but of course at different angles. Okay, so what happens is we'll just connect the red and yellow, blue phases, and that's it. And the neutral would not be necessary because the three currents will balance each other out, which means the resultant current is going to be zero. In other words, we don't need the return path, which is the neutral. So that is the resistance of the windings. I've basically determined that each windings, the three windings that are wound on this motor, they are balanced. And they are 3.1 ohms each. But I'm not sure whether the three windings are touching each other inside or are touching the body of the machine. And that brings me to the next test which I must carry out. And this test is called insulation resistance test. I will be basically testing if the windings are not touching each other inside, or if individual windings are not touching the board of the machine. And if that is the case, then we would not be able to connect this motor to the supply. Because if one of the windings is touching the board of the machine, it means if I put on the supply, the board of the machine becomes live, because this is a metal. So any metal is a conductor of electricity. So the windings must be insulated from the board of the machine from each other. For us to determine that the windings are not touching each other, they're not touching the board of the machine, we need to carry out what we call an insulation resistance test. And that's a very special test where we would need a special instrument called an insulation resistance tester, popularly known as the MEGA. Most people would really know what a MEGA is, but technically a MEGA is an insulation resistance tester. So I've just finished using my multimeter. What I'm going to do now is to switch it off. I can switch it off to save the batteries, but fortunately with the fluke type, this kind of meter, even if you leave it on, after some few minutes it will switch itself off, thereby saving the batteries of the machine, of the instrument. Now, this is our insulation resistance tester. Like I said, popularly known as a MEGA. The insulation resistance tester is an instrument used to test insulation resistance. So we want to see if all the windings are separate from each other, and also that they are separate from the earth or from the body of the machine. So I'll connect one point here first, and then on top of it I'll connect another one, another probe. As you can see, I'm using here crocodile clips. When I was using my multimeter, I was just holding the probes with my hands, and there was no problem. But with this instrument, what is going to happen is that I'm going to induce a voltage, actually a very high voltage, about 500 volts. This is a 380 volt three-phase motor, which means it requires 380 volts for it to operate, to run. So when I'm doing an insulation resistance test, what I will do is I will induce a voltage 2 times as much as its operational voltage. And if it can withstand that, then it means that the machine is good. This is according to the regulations, the IET regulations. They stipulate that if an equipment is operating at a certain voltage, your insulation resistance voltage which you must induce must be twice as much. So this operates at 380, and twice as much would be 600. But this kind of instrument I've got, it has got, you can see here, the voltage range is in red. So it starts from 250, 500 volts, and 1 kilo. 1 kilo, which means 1,000 volts. So 500 is not twice 380, so I'll go up to about 1 kV, which is 1,000 volts. I'm going to induce 1,000 volts to this machine. This is basically like a generator, like a DC generator, so it can generate that voltage, 1,000 volts. So it means when I am testing, I have to make sure that I'm not touching the ends of the probe, because you can actually receive a shock if you touch the ends while it's testing. That's why I'm making use of these crocodile clips. Crocodile clips, I can just clip onto the winding, which I want to test like that, and leave it, and then I'll activate the instrument. Okay, so now I'm going to select a voltage. Okay, that's about 1,000 volts. And for me to test, I must press this test button. You can see it's testing, and it is showing me 1,000, actually bigger than 1,000 mega ohms, 1,000 million ohms. That is the resistance between those two windings. If you have got such a resistance, then you have got good insulation. Definitely current would not be able to pass through one point to the next, because there's a very, very high resistance. 1,000 mega ohms means 1,000 million ohms. That's very, very, very high resistance. And again, if we go back to our IET regulations, they stipulate that the minimum resistance or acceptable resistance for an insulation resistance test for such an equipment should not be less than 1 mega ohms, 1 million ohms. But this one is giving me 1,000 mega ohms, which is very good, almost perfect, not really perfect, but very good. So that's acceptable, the resistance between that winding and the next one. So I'll go on to the next one, the next winding. I'll leave the first point where it is and then connect it to the second one and see again if there's a very high resistance. Once again, I get bigger than 1,000 mega ohms, which means 1,000 million ohms. Very, very, very high resistance. And that is acceptable because it is above 1 mega ohm according to the IET regulations, which we follow. Those are the British standards, which we follow also here in Oman. All engineers all over the world, they talk the same language. So even if you go and peruse Oman regulations or rules, they will tell you the same thing, that the insulation resistance of an equipment should not fall below 1 mega ohm. Fixed equipment. This is treated as a fixed equipment. Portable equipment and domestic electrical installations, those ones would only require something like 0.5 mega ohms. It's acceptable. If you've got 0.5 mega ohms, as the insulation resistance is acceptable in a house or in a commercial building or portable equipment, that is acceptable. But when it comes to fixed equipment like electric motors, transformers, and so on and so forth, those ones require at least not less than 1 mega ohm. So that brings me to the end of testing. I've tested the resistance of the windings. I've tested the insulation resistance of the between windings. Okay. Now I should do another third test, which is called insulation resistance between windings and earth. So now I'm testing the insulation between one of the windings, all of the windings, one at a time, to earth. So the body of the machine can be treated as earth. So I'm going to induce another 1,000 volts between that winding and to earth. So the insulation resistance again should be greater than 1 mega ohm. If it is not, then the machine would not again be able to be connected to the supply. Because what it will mean is if you connect your supply onto this first winding here, then current will be able to flow and come out through this point, which is the earth point, and we don't want that because people who are carrying out maintenance normally touch these machines when they are running. So if the insulation resistance is bad, then they might receive some shocks. Okay, so once again I'll press my test button, and it is giving me a reading of 1,000, bigger than 1,000 mega ohms. Very good insulation resistance between that winding and the ground or earth. Let me see the next one. Once again, I'll press the test button. It is giving me bigger than 1,000 mega ohms once again, which is very good. The last one, which is that one. Okay, I'm pressing the start button once again. There it goes. Plus 1,000 mega ohms. So the machine is clear. It has got good insulation resistance between windings, good insulation resistance between windings to earth. All windings are balanced. That means this machine can be connected to the supply with no doubt, as long as the bearings are sound. Remember, there are two bearings, both ends, one on that end and the other one on that side. So if the rotor can rotate freely, just by pushing it, I can see that the bearings are sound. Then I can connect it to the supply because the machine has passed all the recommended tests. Okay, thank you very much. We shall proceed on looking at how we connect these motors, how we run them, and how we protect them also from certain hazards that might occur. Thank you very much.